In this video, we'll be discussing probability distributions, what they are, how to set them up, and how to calculate certain statistics from a probability distribution. So let's begin with some terminology. First of all, a random variable. All a random variable is a variable where the value is determined by the outcome of an experiment. A probability distribution is a list of all the possible values for that random variable and the associated probabilities for each of those values. So what we'll be creating is something that looks like this. What the row with the value x represents is the outcomes of the experiment. How many times did we see event x? In the case of this distribution, you might have had 0 occurrences of x, 1 occurrence, 2 occurrence, 3 occurrence, or 4 occurrences. And the second row represents the probability with which each of those events happened. So the probability of having event x happen 0 times is 0.08. The probability of having x happen 3 times is 0.23. Now remember, because this is a list of all the possible outcomes for that random variable, so in the case of this experiment, x could have happened at the very least 0 times and at the very most 4 times. With those being all the possible outcomes, well then the probabilities within a distribution have to add up to 1. So if we add all those values 0.08, 0.21, 0.35, 0.23, and 0.13, they must add up to 1. Because all of the possible outcomes of the experiment are contained within that distribution. Now we're going to look at how we would go about creating a probability distribution. So here's our scenario. We have a large population that is 40% female, and we want to create the probability distribution for selecting females from a random sample of 2 customers. And we'll use a tree diagram here to get us started. So looking at our first customer, we could get either a female or a male. We're told that the population is 40% female, so there's a probability of getting a female of 0.4, which using our complement rule would make the probability of getting a male 0.6. Now it said we're going to select 2 customers, so we need a second branch here. The fact that it says this is a large population means that even after we select that first customer out, it's still going to maintain that same probability of getting the second customer female of 0.4 and the second customer of male of 0.6. So due to the large population, our probability for the second customer remains unchanged. If we're to finish off the tree diagram and calculate our terminal probabilities, well, going along my top branch, we have a female customer first and a female customer second. So remember, the operation we want to think of with AND is multiplication. So to find out that terminal probability, we have 0.4 times 0.4, giving us a probability of 0.16. Similarly, looking at getting a first customer female and a second customer male, female and male, multiply the probabilities, 0.4 times 0.6 gives us 0.24. We then do the same for the male customer first, female second, and male customer first, male second. Now when we want to go create our probability distribution, because we're doing it based on the selection of females, we want to look at how many females we've picked in each of those scenarios. So in scenario 1, female first, female second, we have 2 females, female then male, 1, male then female, 1, and male, male, no females. So we now have all of our terminal probabilities with all the possible outcomes for choosing females, and we can go and create the probability distribution that we've already seen an example of. What we want to think about when creating this, what were the total possible outcomes of selecting female customers from those 2 picks? Well, we had no females, 1 female, and 2 female. That was the only thing that could have happened. We saw the probability of selecting no females was 0.36. That was that bottom branch of getting male then male. Now when it comes to the probability of 1 female, we saw that there was 2 ways that could have happened. I could have gotten female first, male second, or male first, female second. So now our mathematical operation will be addition, with two possible ways that could have happened, both ways giving us a probability of 0.24. So 0.24 plus 0.24 gives us a probability of one female of 0.48. And then finally, our probability of getting both females we saw was 0.16. And again, always a good check to go and see. That's all the possible outcomes, so that has to add up to a probability of 1. So if I add 0.36 plus 0.48 plus 0.16, we should get exactly a probability of 1. We could also represent that graphically, seeing the possible outcomes of the experiment on the x-axis. So we either got 0, 1, or 2 females, and the associated probabilities along the y-axis. From a probability distribution, there are also some calculations we can make. We can calculate the mean of a probability distribution with the following formula. Now, again, if we remember what these symbols represent, and it is very important that we do remember these symbols, we get mu, or the population mean, is equal to capital sigma. This represents the sum of, well, it's saying it represents the sum of x, the possible outcomes of the experiment, the values for the random variable, times the probability of x. So we're going to have to take each and every possible outcome and multiply it by its associated probability. And once we've done that, we can add it all up. We can also calculate the standard deviation. And as per usual, our standard deviation formula is a little uglier than our mean formula. This symbol here represents the population standard deviation. And what this is saying, we have to take the square root of, again, the sum of. And now we're not just taking the value for the random variable. We're taking the value for the random variable squared times its associated probability. Once we've done that for each and every value of the random variable, then we add it all up, and we subtract off the value that we got for the mean squared. It should also be noted that if you see the term expected value, that is synonymous with the term mean. So in other instances, we've learned that the mean, we also may see that as average. But it is also important to note now that anytime you see the term expected value, what it's asking you is for the calculation of the mean. So going back to the probability distribution that we created, and now we want to calculate the mean and standard deviation for this probability distribution. Well, if we look at our formula for the mean, the sum of each value for the random variable times its probability. So we take the possible outcome 0 times its probability 0.36, plus the possible outcome 1 times its probability of 0.48, plus the possible outcome 2 times its associated probability. And again, following the rules of BEDMAS, the multiplication inside the brackets first, and then taking the sum. What we should find is that we have a mean of 0.8. Doing the standard deviation, again, there's a little more going on in this formula. But what we need to do now is not only take each possible outcome times its probability, but each possible outcome squared times its probability before we add it. So 0 squared times 0.36, plus 1 squared times 0.48, plus 2 squared times 0.16. And once we've done all that, we'll add those values together, right? Our sum of notation, and then subtract off the value we got for the mean squared. We should get 1.12. Squaring the mean, 0.8 squared is 0.64. We now do the subtraction between those two, and then finally take the square root of the whole thing, and we should find to 2 decimal places we get a standard deviation of approximately 0.69. Here we're going to learn how to use Excel to create a basic probability distribution. and then follow that up by seeing how we can't use Excel to speed up the process of calculating both the mean and the standard deviation within that distribution. So the first thing we want to do is to create the distribution for rolling 2 standard 6-sided dice. And in order to create any distribution, what we need are the possible outcomes and the probabilities of those outcomes. As we roll 2 dice, we have an absolute lowest roll that we could possibly get of 2 up to a highest potential roll of 12. And we'll explore how we calculate the probabilities of each of those possible rolls. If we look at how can we roll a 2, well, in order to roll a 2, we would need to roll a 1 on the first die and a 1 on the second die. There's no other way I can do that. I need a 1 to happen on both of the dice. Looking now at how many possible different ways we could roll a 3, we could potentially roll a 1 on the first die, which would mean we would need to roll a 2 on the second die. But just as likely, we could reverse that. The first die could have been the 2, and the second die could have been the 1. So when we roll a 3, it doesn't matter which order I roll those in or what I consider die 1 and die 2. As long as I roll a 1 on one of the die and a 2 on the other die, both those possibilities need to be considered when we calculate the probability of rolling a 3. Similarly, as we talk about rolling a 4, we need to consider all the possible different combinations on each of the die that could add up to a 4. So those combinations could include rolling a 1 and a 3, rolling a 3 and a 1, or also rolling a 2 on both of the dice, in which case I can't mix up the 2. I have to have a 2 on both die. So there's 3 possible ways I can roll a 4. And we start to recognize a pattern. 1 way to roll a 2, 2 ways to roll a 3, 3 ways to roll a 4. And that pattern is going to repeat itself all the way up until we get to a roll of 7. So there'll be 4 ways to roll a 5, 5 ways to roll a 6, 6 ways to roll a 7. But once we get to 7, 7 is the pinnacle. 7 has the most potential rolls. Because once we get to 8, unlike in 7 where we had 1, 6, 6, 1, 2, 5, 5, 2, 3, 4, and 4, 3, all of a sudden we start going down the hill with less and less probabilities until we get to our final roll of 12. So once we get to 8, as we said, we've passed our maximum number of possibilities of 7 with 6 potential rolls that lead up to 7. With 8, now working back down the hill, only having 5 possibilities, 2, 6, 6, 2, 3, 5, 5, 3, and 4, 4. Continuing that pattern now, declining, 4 potential rolls of 9, 3 potential rolls of 10, 2 potential rolls of 11, and last but not least, the one and only roll that will lead to a 12, which is getting a 6 on both die. So we now know how many different ways we can roll each of these values. But to calculate the probability, we need to know not only the number of different ways we can roll a 2 or a 3 or a 4 or whatever, we need to know how many potential different rolls there are in total. So with 2 6-sided die, we can think of it in 2 different ways. I have 6 potential options on one die and 6 potential options on the other. So 6 times 6 gives me 36 potential options. Or 6 to the exponent 2, the same thing. 36 potential different rolls we have with 2 6-sided die. Or if I wanted to, with us having all the potential rolls listed in front of us, we could count them all. So our probability for rolling a 2 is not just the one way it can happen, but the one way out of the 36 potential different rolls there are. And we'll simply continue that pattern to finish out the probability distribution. So with our distribution completed, a good idea is to check whether we've actually done it right or not. And one good double check is if I understand that there is no other potential role outside of what we've done here, and any probability distribution must include all the possible outcomes, so there's nothing I can roll lower than a 2, there's nothing I can roll higher than a 12, if there's nothing else that can happen outside of this, these have to be all the possible outcomes, in which case all my probabilities together must equal exactly 1, or 100% of the potential outcomes. So a good double check to do if you've created your own distribution is to use this nice AutoSum feature in Excel. And if I click AutoSum and we sum up the probabilities from a potential lowest roll of 2 to a potential highest roll of 12, what we should see is that comes to an exact probability of 1, or 100% of all the possible outcomes that could happen from rolling 2 dice. And now that I know that my distribution is created correctly, we can go on and calculate the mean and the standard deviation of this distribution. So getting some of this stuff out of the way and reminding ourselves of the formula for both mean and standard deviation within a probability distribution. First I'll show us how to do it the long way, and then I'll show you there is an Excel function that does add a bit of a shortcut to it. So for the mean to begin with, what it's telling us the mean is if we remember what these different symbols represent, so we have the capital Greek letter sigma, which always represents the sum of. It's telling me I'm taking the sum of each potential outcome times that potential outcome's probability, and then summing it all together. So the outcome of 2 times its probability, plus the outcome of 3 times its probability, and so on. So if we were to simply create an Excel function that we could click and drag, equals my cell with 2 times my cell with the probability of 2. And if I'm to click and drag that, and remembering what happens as I click and drag functions, is that as I click and drag it one space to the right, my function also moves all its cell references one to the right. So in my one cell over, I've got 3 times its probable outcome, and then over 4 times its probable outcome. So the only thing I would have left to do to finish off the mean according to this calculation, because we've done all of this stuff in the bracket, each potential outcome times its probability, we simply need to add it up now, in which case again I could make use of the Excel AutoSum function, and we should find that we have a mean of exactly 7. If I were to show more decimals, we would see that there is exactly a mean of 7. And if we think about what we learned back in Unit 1 about distributions, and this is a nice symmetrical distribution with a nice peak in the middle, completely symmetrical, well, where should the mean, median, and mode be? They should all be right at that top peak if this thing is symmetrical, which was a peak of a roll of 7 with 6 potential outcomes, and as I go to each of the tails, slowly as we get to our outer limits of 2 and of 12. So it makes sense that we actually do see a mean of exactly 7. Now I'll show you there is a shortcut formula which kind of does both of those calculations that we just did in one fell swoop. So I'll highlight first of all, that was our mean. I could also calculate the mean in a slightly different manner using the Excel function SUMPRODUCT. And instead of me having to manually multiply each probability times its outcome, this function will do that for me as well as add everything together. So I'm going to use the Excel function called SUMPRODUCT, and all I need to do is to highlight the 2 different arrays that I have. So array 1, all the possible outcomes, and array 2, all the probabilities of those outcomes. And what it will do is it will multiply the first item in my first array times the first item in my second array, the second item in my first array times the second in my second array, third in the first times the third in the second, and so on, and then add those all together. Sum product. So product meaning multiplication, sum meaning addition, and Excel understands how to follow the order of operations. So if I do that in one fell swoop, I should get that mean of exactly 7. Okay, in order to calculate standard deviation, there's a few more steps. The formula is slightly uglier, including a subtraction, dealing with a square root. But I'm going to have to start in a similar way. So to calculate the standard deviation here, we would start, again, using order of operations, inside the brackets. Well, now if I look at this multiplication that's involved here, it's not simply telling me to multiply each potential outcome times its probability. It wants the potential outcome squared times its probability. So if I'm going to do this on my own, I would simply say it's equal to 2, or the cell with 2 in it, squared, times its potential outcome. And again, Excel understands order of operations. It knows it's going to have to deal with this exponent before it deals with this multiplication. And again, because I cell referenced everything, I can simply click and drag that all the way along. So the next step here is to take the sum of that. So again, using AutoSum. But we notice at this point, we're actually not done the formula. All I've dealt with so far is sort of this part of the formula. I still need to do is subtracting off the mean squared and then taking the square root of the whole thing, which would be on me to recreate. I've got the sum of everything. I can now subtract off the cell in which I calculated the mean, and I would have to square that. But again, we're still not done. We have only dealt with underneath that radical sign, the square root. I now still have to go and take the square root of everything to finalize this. So one last step, I want the square root of this entire thing. So a bracket at the very beginning, a bracket at the very end, to the exponent 0.5. And now we get to 2 decimal places that we have a standard deviation of 2.42. Again, I could make use of the Excel function SumProduct to slightly shortcut this. So again, standard deviation, if I use SumProduct. So now my first array, I don't want to just use the first array. I want to square that value. Now, if I pull up the function itself, I'll show you that this is actually squaring each individual thing. So I notice right now, as I have my array set to C6 to M6, it lists the values 2, 3, 4, and so on. If I put that I want that to the exponent 2, notice now that it's not 2, 3, 4, it is all those actual squared values. So 2 squared is 4, 3 squared is 9, and so on. The second array again will be all those probabilities. But here, again, we're not done. All we've dealt with is this part of the formula. It would be on us to recreate the remainder of the formula. So minus off our mean squared. And again, we want the square root of that entire thing. So bracket around everything to the exponent 0.5. Hit enter. And again, we should get the exact same square root of 2.42.